You know, every single time you log into an app, this tiny little digital quest kicks off. It's a journey that happens, millions of times a second, all over the internet. So today, we're going to follow that quest, the validation of a JSON web token. It's a really cool hidden story of trust, security, and a whole series of digital checkpoints.
So, picture this. A token shows up at our system's front door. It's basically a digital passport, and it claims to represent a user who wants in. But, in a world full of sophisticated fakes, how do we really know it's the real deal? How can we be absolutely sure it hasn't been messed with? This is the core challenge of digital trust we're going to break down.
And that's where our hero, the JSON web token, begins its quest. It can't just waltz in and expect the red carpet. Oh no. It has to prove its worth by running a gauntlet of really tough checks, and each one is designed to expose any little weakness or lie.
So, this whole journey happens in 4 main stages. First, the token's got to get past the outer gates, right? That's where we do some quick, basic checks. If it passes, it gets into the inner sanctum for some serious security scrutiny. If it survives that, it has to give us one final piece of proof, connecting its digital identity to a real user. And only then, only after all that, is the reward granted: access. Okay, here we go. Our token has just arrived. It's knocking at that first gate, and the system is ready with its most basic, fundamental tests. These are the quick, upfront checks designed to weed out the obvious fakes right away. Before we even care what the token says, we check if it looks right. You see, a valid JWT has a totally non-negotiable structure: header, payload, and signature, all separated by dots. If that structure's off, it's immediately rejected. Game over. This is the first, and honestly, the fastest way a token can fail.
All right, so once the format checks out, we get to look inside at its claims. Just think of these like the official data stamped into a passport. This is the real heart of the token, and it's got all the juicy info: who the user is, who issued the token, and, critically, when it expires.
In that expiration date, that is the very next checkpoint, and it is a big one. It's a simple black and white rule. If the current time is past the token's expiry time, it's invalid, instantly, no exceptions. This fail-fast approach is so important because it means we don't waste a single CPU cycle on an old, possibly compromised token. So our token has made it past the initial gatekeepers. It's formatted right, it hasn't expired. Now it gets to enter the inner sanctum. And this is where the real high-stakes cryptographic checks begin.
Now, inside this sanctum, the first question is, where did you come from? Is this an internal token, one issued by our own system, or is it an external one from a trusted partner? Think of it this way. An internal token is like a colleague walking through the office door. An external one is like a visitor from another kingdom, and they're going to get a whole lot more scrutiny.
So those travelers from other kingdoms, the external tokens, they often arrive encrypted, for privacy. So our first job is decryption, using a secure algorithm like AES-GCM. It's basically the digital version of carefully opening a sealed letter. We can't possibly verify what's inside until we can actually read it. And now, we've arrived at the most crucial test of all: signature verification. This is the cryptographic equivalent of checking the official seal on a passport to see if it's a forgery. It gives us mathematical proof of 2 huge things. 1, that the token really came from who it says it came from, and 2, that its contents haven't been changed by even a single bit. This is the ultimate guarantee of authenticity.
Okay, so our token is now cryptographically trusted. It's well-formed, it's not expired, and its signature is authentic. It has proven what it is. But now we need to answer a totally different question. Who does it represent? And what does this token actually let them do?
See, a validated token isn't the finish line. It's really just the key to the next door. We use a claim inside it, like the user ID, to go and look up the full user profile in our own database. This is that magic moment where we connect this abstract verified token to a real, concrete user in our system. And with that user identified, we assemble something called the request context. This is a super important object. It combines the verified claims from the token with the user's info from our database, their permissions, their roles, all their settings. It creates a complete temporary identity just for this one request, telling us not just who the user is, but exactly what they're allowed to do right now.
Now you can imagine all this cryptographic work. Well, it's expensive for a computer to do. A well-designed system just can't afford to do all that heavy lifting every single time the same token shows up. And this is where we start working smarter, not just harder.
The solution is just intelligent caching. Once a token is successfully decrypted and totally validated, we store that result in a temporary, super fast cache. So the next time that exact same token arrives, we can skip all the expensive crypto steps and just grab the validated result directly. This massively boosts performance, it lowers CPU costs, and it makes sure you get consistent results every time.
So let's just boil this whole quest down to a few golden rules. First, always check the expiry date. Second, make sure all the required claims are actually there. Third, treat those external tokens with the highest level of care. Fourth, cache your results so you don't do the same work twice. And finally, a really critical security rule. When a validation fails, log the error, but never log the sensitive token itself.
In the end, our tokens quest really reveals a fundamental truth about digital security. Trust isn't a single checkbox. It's a whole process, built in these deliberate layers, starting from the simplest format check all the way up to a mathematically sound cryptographic guarantee.
So our token successfully completed its journey, and it got access. But this whole process kind of raises an even bigger question, doesn't it? We focused on how to trust a token after it arrives. But what about its life before that moment? How should we securely issue, protect, and renew a token in the first place? Well, that's a whole other journey. For another explainer.